Hello, my name is Vraj Patel, and today I will be presenting a large-scale deployment of DCTCP. This presentation explains what DCTCP is and why Meta needed it, how it was deployed, and what we can learn from it. A large-scale deployment of DCTCP. The focus of this work is the real-world deployment of data center TCP or DCTCP inside Meta's production data center. The main goal of the deployment of DCTCP was to reduce latency and packet loss for Meta's internal applications. Instead of relying on packet drops like traditional TCP, DCTCP use ECN, explicit cognitive notification, with signal cognition earlier to and more accurately. Finally, the deployment revealed unexpected operational issues, and the paper shares the lesson learned from the deploying DCTCP at such large scale. So, why was this problem important? Meta runs huge distributed systems that depend on quick, stable communication. Even small delay in the network impact user-facing performance. Traditional TCP often build up a queuing delay and causes packet drop, which slow down latency-sensitive workloads. To improve responsiveness and stability, Meta needed a more precision cognitive control algorithm. This is why solving this problem was essential. Main contributions. This work provides four major contributions. First, it documents the full-scale DCTCP deployment across Meta region, making it one of the largest deployment of ECN-based cognition control. Second, the term developed engineering methods for safe enablement and rollback, ensuring that deployment could be controlled and recovered without risk. Third, the paper presented empirical performance data, including the major result. TCTCP reduced retransmission by 75%, which shows significant improvement in the cognition behavior. And fourth, it provides insight for further cognition control research based on the real world or operational experience. Meta's motivations and background. Meta's data center environment had several challenges that made DCTCP necessary. Meta's workload generates many short latency sensitive flow, which require very low queuing delay. The existing cubic TCP caused the queue buildups and delays, hurting application response time. Top of rank or TOR switches had shallow and a variable buffer size, which made cognition worse. The network carries a mix of large throughput flow and small latency flow, requiring more fine-grained cognition control. TCTCP promised lower queuing or occupancy and fewer packet drops, thanks to ECN signaling. These factors made Meta shift from traditional TCP to DCTCP. Now, the summary of goal and setup. To summarize, Meta's large-scale deployment of DCTCP show that ECN-based cognition control can meaningfully improve data center performance. DCTCP helps reduce requiring delay, avoid packet drop, and significant lower retransmission. This improvement led to a better application responsiveness, more predictable network behavior. Now, the further slides will be explained by my teammate.
Hello everyone, my name is Woury and I will present the design and mechanism part of our project. In this session, I will explain how DCTCP works, how it's different from cubic TCP, and why it is mainly used for in region traffic. How DCTCP works. DCTCP or data center TCP was designed for low latency data center networks. Traditional TCP waits for packet loss to detect congestion that often too late. DCTCP instead uses ECN explicit congestion notification. When a switch starts to fire, it makes packets instead of dropping them. The sender measures the fraction of market packet and adjusts its congestion windows proportionally. This fine-grained feedback helps maintain small curve, stable throughput, and low delay. Exactly what large services like Meta and Netflix need for real-time data processing. DCTCP vs Cubic TCP. There is how DCTCP differs from Cubic TCP. Cubic TCP ranks after packet loss, reducing its congestion windows aggressively. This causes delay and co-oscillations. DCTCP ranks earlier and professionally using ECN marks, so it keeps curves short and latency below a millisecond. In short, Cubic is good for the internet with device paths and high latency. DCTCP is optimized for data centers where links are stable and fast. In Meta and Netflix deployment, this results in smoother traffic, better fairness, and lower occupancy. Why DCTCP only for in-region traffic? DCTCP depend on ECN support end-to-end that are outside data centers. It also assumes very low RTT, around 1 millisecond, for accurate feedback across regions or over public internet. ECN signals arrive too late and cause unfair behavior when competing with loose basic protocols like CABIC or BBR. That's why companies like Meta and Netflix restrict DCTCP in a region or intra data center traffic where all devices support ECN and feedback is instantaneous. Now, the next section will be explained by Larson.
Hello, everyone. My name is Larson, and I'm going to be discussing some of the implementation challenges faced by the Meta team in implementing DCTCP. First, the team has to isolate the in-region traffic coming into the data center. We mentioned that um, DCTCP works best on low round trip time traffic. And since there is no explicit marker of in-region versus out-of-region traffic, the round trip time ends up being the metric that we use to sort out which traffic we'll be using this protocol on. There was a implementation question about where, since the data center has so much equipment in it, so much networking equipment, it was uncertain at first where the DCTCP was going to be implemented in terms of like the physical location in the data center. But the team found that the top of rack switches that are immediately upstream of the host machines not only are a natural bottleneck in the data center, but are also equipped with all the technology required to do this sorting and the load balancing and stuff that the protocol requires. Most of this is done through a technology called eBPF, which allows programmers to set up hooks on kernel activities. So every time a packet comes in, it can be inspected. Uh, Metrics can be pulled, and then things like the RTT can be inferred, and then decisions can be made, and the protocol can be applied after the fact. Um, Actually, the next problem that the team encountered was that Cubic and DCTCP can't really just share a switch buffer because Cubic is a greedy algorithm. It wants to utilize the whole buffer, so it will just keep sending traffic until it experiences packet loss, which is exactly what we're trying to avoid by using DCTCP. So that some of that same program, eBPF, needed to be used to kind of artificially set individualized thresholds for both ECN traffic, that is the DC-TCP traffic, um, and cubic traffic through the use of this drop tail threshold, this drop tail notification, which is essentially uh, a notification that says, "Hey, we dropped one of your packets." So it allows you to set artificial endpoints for the buffer storage for both of these classes of traffic. And by doing this, we were able to at least allow these two uh, protocols to coexist on the same shared medium, although there are still some hardware problems that the team noted. One is there's still a problem with incast traffic. This is like a whole bunch of outside hosts call a single top of rack server so fast that there's no time to invoke explicit congestion notification and slow down the traffic because the buffer's already overloaded. That's something that they found was never solved. And there were also some individualized hardware idiosyncrasies that gave the team some issues. And I'm going to go over one of them that has kind of a story behind it. It revolves around an SQL server. Now, what the team found was that during the rollout, um, all the metrics that they were looking for, the retransmissions were down and network utilization was up. Things were looking good, but they were seeing a lot of dropped connection establishments, like handshake. The TCP handshake was not being completed properly in an unusual number of cases. And they were able to find through this SQL server cases where this SQL server was receiving SYN packets, the initial TCP handshake packet, and it was ECN enabled. It was running on DCTCP, and they were sending SYN-ACK packets that were on that were not marked ECN capable, and the SYN packets were being retransmitted and the ACK packets were being retransmitted, which told the team that those SYN ACK packets were not getting to where they were meant to go. And seeing this allowed them to look into the problem, and what they found was there's this piece of equipment called the multi-host network interface card. This is a upstream piece of equipment. It's after the top of rack switch, but before the actual host. And normally a single machine has a single network interface card that connects it. But in these multiple host NICs, two or four machines might be connected to the top of rack switch by this same piece of equipment, and the multi-host NIC has a buffer in it. It's not a switch. It can't make prioritization decisions um, or filter different types of traffic. All it can do is accept traffic and pass traffic. And this created a fairness problem with DCTCP because DCTCP waits for the buffer to fill up a certain amount and then starts signaling, okay, back off, send less traffic. And with this multi-host access card downstream with its own buffer, able to just take packets and take packets and take packets, the DCTCP buffer on the top of rack switch wasn't filling up fast enough. It had secret buffer space that the algorithm wasn't aware of. So it was allowing way too much TCP traffic in and crowding out all the cubic traffic. And this is how they figured this out. The SYN-ACK packets being sent by this one SQL server that they observed were being sent as cubic packets and just weren't being delivered because the buffer at the top of rack switch was just stuffed with DCTCP packets. And this is just like one example of a lot of the problems that the team faced with hardware of different manufacturers that had unexpected behaviors. And I thought it worth sharing. Now, I'm going to pass the presentation off to Mohamed, who's going to talk a bit about the findings and the conclusions reached by the team.
Okay. Hello, everyone. My name is Mohamed, and I'll be presenting the results section of this paper. And so the major results figure in this paper is shown here on the right, and essentially showing that after the DCTCP approach was rolled out, the average queue length in the switches was about 70% lower than with the regular cubic TCP. And this was measured with the normalized retransmits. Normalized retransmits or normalized retransmissions are essentially a networking metric that tells you how many retransmitted packets occurred relative to the total amount of traffic that was sent. And so what this means is that data packets were not sitting in long queues, and so the waiting time and delay went down. Next, flow completion time, which is basically how long a connection takes to finish, improved by about 30% compared to cubic. So with many of the short, small flows inside the data center finished faster, which is pretty great for user-facing services that would depend on these quick types of responses. At the same time, the link stayed very busy, and there was over about 90% utilization. So DCTCP didn't waste any capacity. It managed to keep the network well used and keep the queues short at the same time. And so overall, this slide shows that in Meta's data centers, DCTCP gave lower delay, fewer losses, and still maintained high throughput, which is exactly what you would want in like a modern cloud data center. So in terms of major limitations, first, DCTCP works best for short distance traffic inside one data center, where the delay is very small. It's not really a good fit for long distance cross region traffic. Second, it depends on a special switch support called ECN. If the switches don't mark the packets correctly or have bugs, DCTCP can't properly do its job. Third, it has to share the network with normal TCP, like cubic. And if the settings are wrong, DCTCP might take too much bandwidth or get pushed out by cubic. And finally, all of this makes DCTCP hard to roll out at a larger scale. It needs careful tuning, monitoring, and gradual deployment to avoid any issues or problems. And so generally speaking, conclusions and takeaways. First, the authors consider the large-scale DCTCP rollout a success, but it was more of an incremental one. they didn't essentially flip like one global single switch. Instead, they phased it out gradually by region, monitored the impact carefully, and iterated on the configuration. The ECN thresholds and the BPF policies as they discovered problems. So that kind of incremental safety first mindset was crucial. Second, DCTCP clearly achieved significant reductions in latency and retransmissions, while at the same time preserving high throughput. So compared to Cubic, queues were shorter, flows completed faster, and the network saw far fewer retransmitted packets. And so specifically for Meta's shallow buffer data center design, this was considered a success. However, DCTCP is not a universal fix. It only works well when you can isolate the right kind of traffic, which is essentially these short RTT in region flows. However, when your switches have and hosts have a solid ECN support. Generally, you still need cubic or other congestion control algorithms for long RTT or cross-region traffic, and so you need to be careful tuning so that those classes and traffic share the network fairly. And third, this deployment helped pave the way for newer data center congestion control algorithms such as DCQCN and HPCC. These newer schemas also leverage advanced signals like ECN and in-network telemetry, but the operational lessons from DCTCP, whether it's about deployability, monitoring, or hardware quirks, inform those future directions. And so the final takeaway is you must match the congestion control algorithm to the data center's actual constraints, which are buffer sizes, traffic mix, hardware features, and operational practices. And so those are the major takeaways. Thank you.